Okay, welcome to the last class. I know they are super busy, and I re really wish I can be there in person with you, but San Diego is great. San Diego has great sunshine, great weather. Hope you also, enjoy the winter here. And let's get started. The last class will be on AI privacy, and we have another, last two presenters, so I'm gonna cover for 15 minutes, and after that, Yabrik and David, remember, right? So you two are giving a presentation. So let's get started. What happened here? Oh, okay. Brief announcements. Homework for the last homework due on Sunday. So previously it was on December 4th today, but I realized that today is not a weekend, so perhaps you need more time, preparing for other classes. So you can submit your homework until this Sunday midnight, and you can, not think about it. You can really, start your final project and do something. And the due will be on December 15th. And finally, do me a favor and please finish the course evaluation because this is important to me. And if you want to recognize my work, you want to recognize my course, please do that. I'm sure that some of you have done that, already, and some of you have not, but you already received the course evaluation link. And yeah, please do that if you have the time. Okay. So this contents will be very easy and actually very interesting. So there's like no formulas, math equations, but what you do is to learn what is privacy and why it matters, and then you experience different attacks, different forms of privacy attacks, and after that, different protection ways. Most importantly, we talk about one possible solution, which is differential privacy. And I'm sure that we can stop here because privacy in large language models will take another like 20 minutes. So I will leave this, in all of these contents are on the slides. You can watch it after this course. Okay. So let's get started with the first session, which is what is privacy and why does it matter? So everybody knows that we are living in a big data era, most importantly, massive collection of personal data by companies and public organization driven by the progress of data science and AI. These big giant companies, everybody using applications, online or offline, they are keeping collecting our data, which is becoming increasingly sensitive and detailed. For example, you are using Google browser, Google Chrome, right? Browsing history, purchase history, social network posts, speech, geolocation, health. But it's sometimes shared unknowingly and without a clear understanding of the risks. Because everybody, every time you download a new application from App Store or from Google Play Store, they typically give you a very long list of this kind of end user license agreement, which nobody actually will pay attention to, and you basically just hit consent, right? Agreed. And then you really don't know how they will deal with your data. Most importantly, your private data. So that's what privacy matters. One example here, if any of you, this company, which is called Baidu, like the Chinese version of Google, like the number one search engine company in China, this is the CEO. And by the way, I'm in the same high school with him, back to my more than 10 years ago, 15 years ago, I'm in the same high school with him. And he's like the very, very famous big hero in our high school, okay? Because, he's the CEO of Baidu. But unfortunately, in 2019, you see, this is a news link from 2019. He made this kind of assertion saying that if they refer to Chinese people, if Chinese people are able to trade privacy for convenience, in a lot of cases, they are willing to do that. So he basically says Chinese people don't pay attention to privacy, which I would say is true. Okay, so because actually most of the Chinese people actually don't care about privacy, but with many teenagers and youth, we are growing up, we know that privacy is becoming more and more important. So right after he says something about that, and this is the video that in his talk, he's presenting some products on behalf of Baidu that he was like attacked by a guy. You can watch the video. It's very interesting. You see that's directly, and he's on the stage, and that guy just came from nowhere and pour him some water from the head. And then what he said is that, what's your problem? Okay, so that's very interesting because a lot of people actually they don't, including me, we don't like this company because this company does not really respect your private data, and it actually trades your private data with the large companies to make money. So that people don't like this company, but in the end, a lot of people still use it because you don't have any other options. Okay, so that's one example showing you how privacy matters increasingly, especially for young people in China. And what happens? I think next slide. What? Okay, and more example on the left. I'm sure you have heard of this. Back to 10 years ago, Edward Snowden and as a PRISM project, which is a large scale surveillance program, not just for the U.S. but for across the world. But and then the story came that Edward Snowden escaped to Russia, right? That's like some like big privacy leakage in history. And on the right, it happens in 2024. Remember, was when ChatGPT was launched, and a lot of people actually tried to use GPT at work. But it turns out Samsung employees they use GPT at work and unknowingly leak critical source codes, which directly violate some company confidential laws. So this is actually some bad cases that you unconsciously leak your information, your private information using other kind of services. This is actually the real examples happening every day. So when we talk about privacy, confidentiality, and security, so there are some like concerns or like some misunderstanding what is privacy and what is confidentiality. So physiologically, confidentiality equals to you don't tell. Like you cannot tell it to anybody. But privacy really means don't ask. It means that privacy belongs only to you, that your right to be left alone from the public scrutiny. But uh, by contrast, confidentiality is about promise from people who have privileged access. So these two terms, they seem similar, but they are not actually referring to the same thing. And finally, for security, because when we talk about privacy, and you'll see a lot of online talks or a lot of materials, they usually connect privacy with security. So you can see a lecture about privacy and security, but it's not the same. So security is to prevent risks due to unintended system use, and privacy prevents risks due to intended system use. So these are the main differences between these three terms. So you pay more attention to them when next time you see. And from the global level, United Nations actually they have the Universal Declaration of Human Rights. This is directly from this Article 12. You can see no one shall be subject to arbitrary interference with his privacy, family, home, or correspondence, blah, 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 blah. So actually, this is like some kind of human rights defined by the United Nations. So like the globally aware, not just for one particular country, one particular region, but actually across the globe, that they claim that this should be a very standard human rights, okay, for privacy. And it turns out for the US, there could be some interesting dilemma. So this is Article 1, Section 2 of the US Constitution that requires the US censors to count individuals accurately for tasks, such as congressional appointment. So this is like it requires that you to count accurately, like assemble all of your information. But it turns out that the Title 13 of the U.S. Code, it says it is against the law for any Census Bureau employee to disclose or publish any census or survey information that identifies an individual, blah, blah, blah. So did you see these two goals actually, they contradict with each other. So this is very interesting. Like, what should you do when you are in this circumstance? So just to let you know, this thing actually it exists. I don't know if they have fixed this two part, but actually now you see some inconsistency happens here. Okay, for privacy, it means privacy actually this boundary is very hard to define, and it takes more time, takes like more efforts to clearly define what is privacy and what is its clear boundary. Okay, so okay, another one joining. Okay, and the scientist needs to have access to data, but On the very top end, it's privacy law. We have different privacy regulations prevent you from directly access privacy data. But from the above, from the bottom, people's awareness of increasing privacy, that the people pay more and more attention, especially the younger and younger generations. They learn a lesson at school. They know privacy is very, very important, so they pay more attention, increasing awareness between the law and the increasing privacy awareness, we do something. So that's what scientists can do. You cannot break the law, and you cannot just offend people by intruding their privacy. So what we do is in between, we do a lot of study to try to make a boundary of our work to do things like to study food safety. But in food safety, you need to access people's information, what they eat, what they drink every day, right? So this is kind of privacy data and how you understand how their brain works. But by understanding, we mean you need to record how their brain works. Like what did you do every day and where did you go? What did you eat? But this also requires to access some sensitive information. And you do some medical diagnosis, clean energy project, epidemic forecast, especially COVID-19, and you do some product detection. All these kind of social information or social computing solutions requires to access some sensitive data. So there is actually no clear boundary between what is privacy and how should you do without clearly referring private information. So that's how you do research. There's some kind of bargain. You need to bargain should be achieved, but it's very hard. So in the real work, in real research, including what you're doing right now or what you're going to do in the future, you should pay special attention to the private data. Also, you should, when you are collecting people's information, it's very important that you let them know they are, being collected so that you can do your research and without, intruding any people's private room without, the compromising the privacy law. Okay, so this is something we learn as the research scientists. And you may wonder that do we really need the science for privacy? So we just remove the personal identifiable information, which PII, personal identifiable information from the data set that is de-identified. So you just remove all kinds of sensitive information, but still do your research? So we can only see maybe the aggregation of all the data, but not any one particular data. Can we just do that without intruding any private data so the privacy will be well protected? So that is a question you can think about it. Can we really do that, or does that really 100% useful? And secondly, there are many like security multi-party computation or MPC. You perhaps have heard of this word. And the federated learning, which stands for FL, have made it possible for the big companies to train the machine learning models with my data while keeping my data on my device. So like they really don't directly access your information on the cloud, but they can still collect enough information to help them train the model. So these two possible solutions may suffice, but it turns out some bad things could happen. Okay, we'll talk about that later. But now let's pay attention. This is one algorithm that very, very, very important for privacy. So it's called multi-party computation or MPC. Was actually developed by Andrew Yao, who is like the Chinese computer scientist and won a Turing Award in back to 25 years ago. Okay, he's actually now in Tsinghua University. So this is the essence of MPC. Actually, it's very interesting. Like you perhaps have ever heard that when you talk about AI privacy, talk about the computation and talk about this kind of encoding thing, there's a lot of math. So it indeed a lot of math, but we are only telling you that this is not math. This is actually very interesting. So think about this situation, okay? There are three people, Alice, Bob, and Cynthia. So we want to know the average salary of their work. Like you see, the ground truth is that Alice she earns 11 per hour, Bob is 12, and Cynthia is 22. That's the ground truth. But we want to know their average salary without knowing, who contributes to what. So like we don't know that, and we don't want to explicitly trigger these kind of query. Like we don't know Alice, we don't know Bob, we don't know Cynthia, we don't know any of them, but we want to know their average. So what we do is to go through multi-party computation. So how we do it is very easy, like and interesting. So the step one is to break hourly wage into four numbers and assign one to each of the four entities. Okay, so for example, Alice is 11. So we split 11 into four parts, like 2, 1, 4, 4. You sum them and you get 11. Okay, you split each number into four parts. And secondly, we distribute numbers to each person. Like, Alice, we assign two, and one will be assigning to Bob, and this four will be assigning to Cynthia, and another four will be assigned to another trusted third party, which is like, you can send up this as a delegate, okay? Trusted third party delegate. So, doing the same thing for Bob and Cynthia. So then you get this kind of thing. So like Alice, her shares are 2 for 2. This 2 comes directly from her salary, and this 4 comes from Bob, and this 2. No, sorry, this 4 comes, I think, from Cynthia. So, but Bob and Cynthia contributes to the 4 and 2 here. So the sum is 8, and the sum is 7, and the sum is 14, and the sum is 16. So you get the average, like, average for Alice, average for Bob, average of Cynthia, and average for the delegate. And you get this that average, and then you just simply sum this average to get the final average of 15. If you do the math, you can say 15 is literally the average of 11, 12, and 22. So this is the very, very, very easy pipeline of how you conduct a multi-party computation. So you see in this way, nobody can ever know Alice is 11, Bob is 12, and I think is 22, but we can also know the average wage of per hour of this Alice. So this is like very interesting. So the multi-party, but multi-party is more than that. Okay, this is just to show you you can actually do that. You know their aggregation without sacrificing any of their private data. So that's MPC. And federated learning is another solution. Like you don't directly contribute the data to the cloud. So the situation is that, okay, everybody has a smartphone, like smartphone one, smartphone two, and smartphone N. You have many, many, many people. You want to train a very powerful model. But according to our experience in machine learning and AI, we know, okay, you want to train a very powerful model, you need to collect a large number of data, right? A large number of training data, X and Y, and you fit your data through a machine learning model, a deep learning model. But you cannot access their user information because they're private. They're in their local phones. What we do is, oh, you don't upload all their data to the cloud because you will access their information. What we do is, okay, how about we just keep their own data on their local device? So they train their own model on their device. So, but the assumption is that their device is powerful enough, okay, powerful enough to train a small local model just based on their data. And then, this phone trains on the local data, and this phone trains on local data, and all the phone trains on their local data without exchanging to the cloud. But how we collaboratively learn from their experience, what we do is, okay, we don't share data, but again, we share model. By sharing model, we mean what's important for a model. Of course, it's parameters, right? The model parameters, we can learn from the parameters of all the models. And those parameters, they are abstract enough because they're just parameters with nonsense to a real human being. If I give you the weights of ResNet or I give you the weights of GPT, actually it means nothing to an ordinary people. So it clearly carried out some meaning, but not meaningful enough to identify some sensitive information. So we exchange the model weights, model parameters, or even model gradients to the cloud. And then the cloud will do the aggregation of those models, for example, averaging those model weights. And we get a new model, right? We get a new model on the cloud. And then you distribute the model to all the clients here. And then they got their model updated. Because on their local data, the local trained model is powerful, but not so powerful enough because it does not have the contribution of all other clients. So what we do is we do the aggregation and then we have the powerful model. So this is how federated learning works. And if you are interested in doing research on federated learning, you can really do that because these years, especially since the launch of GPT and large language models, FL turns out to be a next wave. Like because nobody wants to trade your information to the supercomputer. So you protect your own data, but you still want a very powerful model. So that's something you can do for, at least for research. Okay, it's increasingly popular. So do you think that's enough? Like, okay, can you just get a aggregation information without, losing any private information? But that's, not correct. One example here is this article. Just it says just the 6 days of stepped counts are enough to uniquely identify you among 100 million other people. So this is crazy. Like, okay, so step one is I have some like log information when I'm exercising. So how many steps was day one, day two, day three, day four, day five, day six. So these are my steps. So like, nobody will recognize you based on solely on your steps, right? But it turns out they can. So someday, you post something online, like on Facebook, you said achieve weekly goal, check out my performance. These are the steps. Like these are on your Facebook. You do that, right? You do that intentionally. And then somebody they started to do the bad thing, and the bad things that will, it literally trigger this kind of pattern and they link you based on your information to their kind of large data. So this is kind of bad guy. They have access to this kind of database and they will locate your information by just comparing your six step counts. So this is actually, it's real. This is the link of the research. So this is telling you, you think steps are not sensitive, but actually it is in the viewpoint of some bad guys if they really have access to larger database. Okay. So, in summary, privacy in the big data era is actually very important. Its improper disclosure of the data can have adverse consequences. And by adverse consequences, we mean that your credentiality has been compromised. There could be some safety risks. Okay, and credentials is example your credit card number, home access code, your passwords can be hacked into stealing personal property, which is the common risk. And your identifiable information can also be compromised. For example, your name, your bank information, your biometric data, and finally, information about the individual, for example, your medical status, your religious beliefs, your political opinions, and your sexual preferences. And some of these risks can affect anyone. Even if you think you have nothing to hide, so you're clean, you think, okay, I did not do anything bad, and didn't, I'm a good guy, I'm a law-abiding citizen, right? You think we have nothing to hide, but they can still do some bad things you can never imagine. Okay, so that claims that privacy actually is very, very important. So if only in person we can share something, but now we will skip this sharing session of our own story about privacy leakage. And now we're in the second part, which is privacy attacks. And privacy tags, what does it mean? It means, okay, you are the individual data subjects. You are contributing your data to some online algorithm because this online algorithm could be any platform, like it's TikTok. It trying to optimize for the recommendation system based on your data, your inputs, and other people's data, right? And data users like the government, researchers, companies, or the bad guy, adversary guys. Okay, they are operating, they are manipulating using these kind of online algorithms because most of the online platforms they have the public available APIs to be used to do the web crawlers and to do some promotion. So they can query through the online algorithm, the platform, and then they get answers. For example, they get some aggregation statistics, they get some machine learning model, they can use your model to do something. So what if this bad guy can do something bad, but you still want to use the platform because you want to use TikTok, but you want to protect your information against these bad guys. So the goal is to maintain the balance, like to achieve utility while preserving privacy. So this is something we do. Like this is separate from serious concerns like unauthorized access to the system. So we need to develop ideas to do this. But if you have an idea that's actually, an attack, so this is something you do. Like first step you can think of is, okay, I will never leak my real information, my real name, for starting from my name. Like, do you think that anonymization is safe? But it actually not. So you can just not removing your personally identifiable information before publishing data and you think you're safe. Okay, so because people can really dig through this kind of information. So this table is actually very famous. It shows some names, right? The name, birth date, zip code, gender, diagnosis, blah, 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 blah. So in this table, there is a name called William Wells. If any of you are from Massachusetts or any of your relatives are from Massachusetts, you will see this guy is actually the governor of Massachusetts, back to many years ago. Okay. So this actually tells you that he got cancer. So he certainly, as a public figure, he certainly does not want to let public knows and he has cancer, right? But this is some kind of the information that he wants to protect. So you may wonder, okay, can we just, hide the name of William Weld so you don't know who got cancer, right? So that's our like first insight. But do you think that's really safe by just masking your name here? It turns out no, because there could be some susceptible linkage attack, like the first term, okay, linkage attack. Like we can uniquely linking a record in even in the anonymized dataset to an identified record in a public dataset. So here the linkage belongs to zip code, birth date, and gender. So there is some kind of census and estimation that they are saying that estimate 87% of the US population is uniquely identified by the combination of their gender, birth date, and the zip code. So imagine 87% is basically all of the US population. So everybody is actually, accurately, locatable through your zip code, birth date, and gender. As long as somebody have these three information together, they can locate you, they can know who you are. So in the late 90s, and this team, they managed to re-identify the medical record of the governor of the Massachusetts, that the William Weld, that guy, okay, using a public voter list. The public voter is a public because you're a voter, it's public. And they link those two data sets. Like dataset one is your anonymized medical data, and dataset two is the public voters list. And in these data sets, there are the joint relation of zip code, birth date, and gender. So they can immediately know who got cancer, even if you choose to mask your name in dataset one. Okay, so now you know anonymization is never safe. There should be like more attacks and more solutions to protect your information, but not just masking your name. Okay. So this is how the matching happens, right? So the voter registration list, the birth date, gender, zip code, these three terms. If you learn some basics of the SQL, right? You know how to write the select birth date, gender, zip code, so I'll select something from this table and join by the birth date, gender, and zip code, so that you can immediately have the full table by joining these two tables, right? So this is how you do this linkage attack, basically through the SQL language. So now you say, okay, I'm not leaking my information. So how about the aggregation? Like I don't explicitly, tell people my accurate information, but the companies they only know is the aggregation. So that safe? So now you see aggregation is still not safe. So there are four different attacks actually, even if you only contributing to the aggregation statistics. The problem one is differencing attack. Like you can combining aggregated queries to obtain precise information about specific individuals. Okay, so you can do the combination and obtain precise information. You basically compare. So this is basically similar to the linkage attack. So you have two tables at least. You compare and you know the difference, and then you can know who is who. So that's the first attack. And the second attack is called membership inference attack or MIA. So this is like rather popular than the first one. So it's just inferring the presence of someone in the dataset from a high dimensional aggregating statistics. Like you have a ton of anonymous data. So you do some inference, like oh you infer, okay, this guy could be from this table or not. So you design some algorithms to do the inference attack. So this is IMIA. You can still do that for large language models today. And problem three is reconstruction attack. Okay, reconstruction attack means that you can infer parts of a data set from the output of many aggregation queries. Then this is actually very interesting. I'll show you an example later. And number four is model inversion attack. Like you recover information basically according to the training data of the model. So the like you know what is their training data, even if you don't know exactly what is the training data, but you can do the infer. Okay. So the first one, inference attack. This is the more like the linkage attack. Okay, so one example here is the Netflix challenge starting in 2006. That's the tackle style competition designed to improve the movie recommendations with 1 million prize. Okay, so they released a data set consisting of 100 million movie ratings, rating by anonymized numerical user ID with dates, and researchers turns out that they could identify 99% of users who rated six or more movies by cross-referencing with IMDb, where people post the reviews publicly with their real names. So they're basically some linkage attack. So they do the comparison between the Netflix database and IMDb database, and they immediately know who you are, who writes six or more movies. Okay, so that's the difference in attack. And reconstruction attacks is something about math. You can actually recover the microdata by comparing attributes. So imagine you're given this table. The first row is the group number 1A, 2A, 2B, 2C, and 4A. Description, the count, and age median and age mean. So I'm asking you a question that uh, can you infer the age of the black AA male? So you see this black AA, and this is a black AA female. So my question is, can you infer black AA male? So certainly something you can do is you do the comparison here and you can reconstruct according to these groups of information, right? The black AA male, you see it could be like the subtraction from black AA and black AA female. So you do the math, like 84 equals to 48.5. It's this number, right? This number it times 4 because we have 4. And the 36.7 times 3, this is female. So we do the math here and you immediately get the information of the male. So this is some kind of the privacy leakage because we don't offer you any information of male, but yeah, you can actually do that. Okay. And another like more math focused task is you can design this kind of linear equations. So you can solve them. So what does it mean? It shows you like, okay, we have these kind of aggregation tables, like the age less than 18 or larger than 18 and gender, employee and account and X1, X2, X3, X4. So we treat each row, each column as a variable, X1 to X8. So we want to know, okay, do you know X1, how many contributes to X1 and how many contributes to X2? We want to know exact count, not X1. We want to know if it's 1 or 2 or 3 or 4. So we make them as variables and then we do the marginal contribution. Like marginal means we do the aggregation for less than 18 and employee yes, so we do the count, and less than 18 employee no, we do the count, and you get immediately the marginal contribution of the age and employee. And then you can solve this linear equation system like x2 plus x4, 2 plus x4, this should be less than 18, right? So this should be around 2 because according to this table it is 2. But what you do here is that, okay, I'm going to allow some flexibility. It's not directly equal to 2, but there's some flexible, like 2 minus epsilon. So epsilon could be extremely small, and it's a real number. It's extremely small. But what I'm doing this is to make this system more flexible and more solvable because I'm going to have like x2 plus x4, x5 plus x7. We have a list of these equations to satisfy each equation at the same time. So we allow for this kind of flexible constant. So we do and we make the solution of this linear system, and then we can immediately have the number of x2 and x4 because X is like the real number, so we can solve them. So this is how you do the reconstruction attack. So in this way, there is a survey saying that this kind of thing, this linear equation system can actually reconstruct 17% of the data of Americans. So this is amazing, right? You don't know, even before we're reading this part, we don't know by only giving you information of age, gender, and employee, you can still do many, many, many things by listing this linear equation. And then membership inference attack. So this is very easy to understand. So because most of the models are trained on a private data set, we do the summarization models, they could memorize the PII information in the training data. So they are trained on a private data set, but can still leak some private information by some malicious query. So here is how it goes. So this bad guy asking, was this specific data record part of the private training set? So it referenced some data, do the query through the prediction API. So the model will just do the query in the training API to the private training data. So this is how it works. You can infer, like, you do millions of queries. And you perhaps you do the permutation of all the sensitive information from this bad guy, and he asks the model many, many, many times, and the model will, leak some key information if it, was trained on such kind of private information consisting of the bad guy's query. Okay. So that's the detailed problem definition. We're not, listing them here. So the key here that you do this kind of fake query. You pretend that you are coming from the good side. You pretend you are from the in distribution data set. So you do the query and you fix the query, and then the model will believe you are one of them and will give you some answers based on your future query, even if the future query is a malicious one. Okay. So here's the example. You pretend that you're Bob, you want to launch the attack without knowledge of training data, but has access to the model API, like you have access to Gemini API, GPT API, but you don't know anything about the training data. You want to infer what it could possibly be in their pre-training data. So the assumption is that you have some in distribution data. In distribution means that you know which kind of data set is the model prefer. It could be the model generated data. Like you know the style, exact style of GPT's generated data. So you pretend, oh, I'm from your distribution, so I'm asking the same question. So you're gonna answer me in the same way. And then, I can mimic this kind of study by easily replacing my in and out data to some kind of malicious sensitive information, and your model can still answer because you are triggered, like tricked by me. Okay, so this is the essence of how you work through this shadow model. And finally, this model inversion tag is like easier to understand. So it tells you that even if we don't release the raw training data, the weights of the training network might still reveal the sensitive information. So this figure, like on the left, is the real face, real human face in the pre-training data set. Nobody knows because they only trained on this data set and never release any public information. But in the end, we can do this kind of model inversion attack to recover information. Like we can do the kind of recovery, this kind of recovery, and then finally you can compare the last row is their recovered face. So you can compare, they're very similar, right? They're very same. So the column one's training image and column five is the reconstruction image using classification network. So the example here that you given a classifier and you do the query and through gradient descent or gradient ascent act as some adversarial attack. You keep asking, oh, do you think this phase will cause the gradient to be smaller and smaller and will cause the loss to be smaller and smaller? If it is, it could be in your training data, or at least have the similar distribution of your training data. So we design a lot of the tricks to do this kind of attack, and then you will be able to get it recovered, okay, through this kind of model inversion attack. So this could be, you know, leaking very, very, very private, sensitive information because that's your facial information actually. So you can replace this facial information with any other key information like, your bank account number and more of your medical records, something like that. You can do the similar thing. So this work was published in more than 6 years ago, but you can imagine they can do that 6 years ago, but what can they do now, right? So they can actually do a lot better. So this is model inversion attack. And the third session is on differential privacy or DP. It's very popular. So a brief history of protecting people's privacy. Actually, it's not starting, recently. It starts back to the 1970s when we have statistical disclosure control. So we do the data sweeping, like we sweep different data, and that was actually implemented in the consensus. Okay, like we want to get the aggregate information without explicitly telling you who you are. And back to 25 years ago, we have different measures like key anonymity, eye divergence, T closeness. I even don't know what that mean, but you see these terms are developed to protect your sensitive information. Okay. And since the year of 2006, the differential privacy was invented by these four scientists. Okay, and they win the 2017 Godel Prize winners. If you know this prize, you know it's very prestigious. It was an award to have a recognition of scientists who made a significant contribution to like protect the user information for the computing industry. So these are the four professors: Dork, McSherry, Nissim, and Smith. So they co-developed the idea of differential privacy. Okay. So what does it mean? So why do we have DP? So the motivation is, okay, we want to have some indistinguishable information exchange. So we want to exchange information, but we want to make it as little as possible. So we only change a little information of the original data that will lead to indistinguishable output. So an example here that we have the original dataset D. So you want to protect the information, the sensitive private information of all the people in the dataset D. What you're gonna do is you do a very slight change. How about you replace Alice with another guy here without changing any other person's information? And through this kind of algorithm, when the adversary trying to locate some information, it will ask the question, is it really from D or D prime? The D prime is the new data set. So it cannot distinguish between D and D prime, something very similar to adversarial attack, right? You cannot distinguish by doing this very slight replacement. So what they do is, okay, we found this kind of mathematical equation. We designed this system to be a very stochastic algorithm. So you look at the figure here, we have this algorithm, and we claim that dataset D and after the slight replacement, another dataset, those two datasets, they go through our stochastic algorithm A, and after that, we have the modified version of the data. But the great thing is that after this certain algorithm, those two datasets, those two distributions, they are very indistinguishable. So you don't know who is who by this very slight change. So this is the like how you enforce it mathematically. So D and D prime are the two data sets or the two distributions. So the probability, the fraction very small, very small because the epsilon is very small. You see, these will be very close to one, but not exactly one. So in this way, it will guarantee that, okay, today you have the original dataset D, but you design this stochastic algorithm and then it was replaced and transformed to another version, but they are very similar. They can still to be used in all circumstances, but that guy cannot access any sensitive information to locate who is who. So this is the essence of the differential privacy. So the key here remains, okay, I know how it works, but how do I design this stochastic algorithm A, right? Because this algorithm is not a random one. It should be manually designed to make sure that this equation helps. So that's the result. The result is that like, these two distributions are very similar, but they have the ratio of very small and close to one. Okay. And this is an example to show you how actually we can identify some information because this is math. We can clearly know the exact probability of leaking or not leaking your private information. So this is an example you can see later. And how to add the noise? So you can do the Gaussian noise, you do the ad, but it turns out the Gaussian noise does not work very well. So what you do is, okay, we can do the Laplace noise. The Laplace noise is the like advanced version of the Gaussian noise. So we can explicitly add this noise to your data set, and your data set will not change so much and still can contribute to your model training. Okay, so this is how we do that. And you can also do the noise addition in the categorical case where they are not real numbers, they're just yes or no. And this guy will ask, do I look at Brad Pitt? And you will add some noise to make sure you don't know who is who. Okay. So in this way, we do some randomization, like we toss a coin. Like the answer yes, we toss a coin with probably 20% of being ahead, you can change it to yes. And with 80% probability, you can change it to random yes or no. So this is randomly, total random. So in this way, you can protect the original information. Like if it's this, it has 20% of being yes, and another 80% of being yes or no. It's totally random. So this is like 50-50, and this is 20 to 80. So this is how we protect information, how we inject noise to protect their ground truth yes and no for the categorical information. And there are many application scenarios. Like we can use differential privacy for building databases. Like we only answer aggregate queries, but we don't answer queries for a specific user, for specific table query. We add noise into the query results to protecting privacy. For example, Microsoft had this PinQ database, and Uber had this cross information database. So that's for the DP database. And we can also do the DP machine learning. We can add noise into the machine learning algorithms. For example, TensorFlow has the privacy part, privacy module, the data set, and training in machine learning algorithm. And in training, we add differential privacy to your private data, and then you can train a model. You can still train this perfect model, but you cannot do the model inversion attack or membership inference attack by easily using the existing algorithm because we add DP here. And it turns out we can do that in the deep learning standard gradient descent. So this is gradient descent. Well, how you do that is that you can easily inject this one to the SGG, which is called DP-SGG. So that's the paper called Deep Learning with Differential Privacy. So basically what they do is, okay, we can inject these updates of the noise. You see this is add Gaussian noise. So adding this noise will not affect the performance of your network too much, but they can help protect the information. Okay. And this is actually, co-authored by Ian Goodfellow, the godfather of GAN, if you remember from previous lectures. Okay. And we can also design the DP-based data collection algorithms where random responses may apply. You see, this is the users and this is the server. They will aggregate information, and we add explicit noise to help protect their information. And we can also design the DP-based data synthesis. Like we can do the modeling based on original data to get the statistical model. And we can also add noise into the synthetic data from the statistical model. For example, the US consensus data is that we have the original data when we construct this model. And from this model, we sample some synthetic data. So the synthetic data is not from the real data. It's synthetic, but it is some reflection of the true original data. Like the two distributions are very similar. So you can do a lot of things actually based on the synthetic data. By the way, the synthetic data or data augmentation is still one of the most popular research direction in the area of large language model. So we can count on the synthetic data to train powerful reasoning models in these days. And the real application, you may wonder, so DP is very useful. Are there any big tech industry that directly use it? So there is. So that you can see Apple, they use differential privacy on your iPhone, on your MacBook, on your iPad, and Google they use this information like in the settings of the Chrome. You see there's a clear setting. See the statistical Google they use this DP to aggregate your information. And LinkedIn use the privacy preserving analytics and the reporting and linking. So there's a US Census 2020, so they adopt differential privacy. So that's some real user cases. So you now see different privacy is actually helpful, and a lot of companies, government, they started to use it. So that will for all for the today's class. And the last session is privacy in large language models. We will not, deliver this talk, but just to trigger your interest. Okay, you should know her, right? So nobody, actually know the connection between Taylor Swift with privacy protection. But here's a paper called Taylor on Swift, like secured way to release for large language models via Taylor expansion. So they use Taylor expansion. This Taylor is not this Taylor, right? So this Taylor is the famous mathematician called Taylor, and they use Taylor expansion. So they call their paper titled Taylor on Swift. Like you can directly draw some links between this Taylor and this Taylor. So that's the paper we're covering in this talk. You're welcome to read it. Okay, so that helps you to protect your information using the Taylor series. If you learn it correctly, that you can easily, do this decomposition of the model weights to represent any function using the Taylor series, and then you can do the information protection. Okay, so that's all for this course, and then we have two presenters, and